that you haven't received a partner just yet, and I will send you a message with your partner. Otherwise, yes, assignment two is due this Sunday, and yeah, there will be office hours before and after each lecture, including tomorrow, and there will be work periods on Friday and Saturday. As for tomorrow's session, we will have a case study, and they will be talking about algorithms and data structures in the projects that they work on at Bell, the telecom company. Before we jump into today's session, which I really like, so today's session is very practical, and it uses the techniques. Let me just adjust my microphone. Um, yeah, so that should be better. Today's techniques are very practical, and we'll see kind of in bad situations where you have to deal with poor algorithms, how can you still make the best use of your hardware? But before we do that, we will just cover the last bit of yesterday's session. Um, because we did fully complete yesterday's session. Yeah, so yesterday we were looking at graphs and we looked at the breadth first search algorithm for a graph. In the case for the way that a breadth first search algorithm works for graphs is we maintain two lists. One is a visited list and one is, is a queue of all of the nodes that we have to yet visit. So the way it works is we first add the root node to both of our lists, to our queue as well as our visited list. And then we add the neighbors, making sure that they haven't already been visited. So we check the visited list. If they're not in the visited list, then we add them to the queue as well as add them to visited. And then we visit the first element in the queue, we pop it or we dequeue it, and we kind of repeat this procedure, making sure we add all the neighbors that haven't been visited yet. So we also looked at the implementation of this algorithm. We went through it fairly quickly, so we'll slow down and look at it again. Um, the the way this algorithm works is in the very beginning, we create our two data structures. So our set, which is the visited element, and then our queue, which contains just the starting node to begin with. Then while the queue is not empty, we remove the first element in our queue. So we remove that. And if we have not visited this node just yet, then we process the current vertex, meaning we do whatever we want in our traversal. Then we add it to our visited set of visited nodes. So this will ensure that we won't visit again in subsequent calls, because this if condition only evaluates if it's not in the visited set. Keep in mind that since we did use a set, this is also an O of one operation. Okay, so we visited our node, we've added it to our visited set, and now we just need to add all of the neighbors that have not been visited. So for neighbors in the graphs, neighbors, if the neighbor is not in visited, we add it to our queue. And then we go back to the start of the while loop and we dequeue the while loop starts up here. We start from here and we start from the beginning of the while loop, which the first step is dequeuing the next element in our queue. So eventually we'll remove all of the elements in the queue, and once we've done that, we've traversed the entire graph. The graphs do make an assumption that it is a connected graph, meaning there's no kind of islands like this. If there's an island and we start a breadth first traversal here, you can't expect to reach here because we're traversing just the edges. Okay, so we looked at running this. We saw that we got the right output. Next, we can also do pre-order traversal using the same graph. So here our approach is slightly different because we're using recursion. And the idea is a bit similar in the sense that we maintain a day structure to maintain all of the visited nodes. But in this case, we are using it as a parameter to pass between recursive calls. So we have this set, it maintains all of our visited nodes. And what we do is if visited is none, we first create the set in order to maintain it. And then we visit our current node. We add the current node to our visited set. And then for all of the neighbors, we do a recursive call of visiting, visiting, oh, sorry, of traversing all of the neighbors. But the key thing is that the visited data structure is going to be common between all of the different recursive calls. It's going to be the same set. So once we visited a node, we're making sure that we add it to our set of visited nodes. And that way we won't ever recurse on a node that's already been visited. So this is a recursive definition of a graph traversal, and it's pre-order as well, which means if let's say this is our graph, and we start at this node, if the first, if the first node of the, sorry, it's pre-order, meaning we first visit this node, and then we visit the children. And then in each traversal of the children, we first visit this node and then we visit the next child. And then we visit this node and then we visit the next. Sorry, I say child, I should be saying neighbor. But as a result, the main thing with the pre-order traversal is we visit the current node before moving on to the neighbors. And this is the traversal that we get. Oh, sorry, I should start from here. So if I do the pre-order traversal, we go from 1, 3, 6, 10, 7. So 1, 3, 6, 10, 7. There should be, I think in the graph that's being declared here, there is a line between 6 and 10. Sorry, so it is 1, 3, 6, 10, 7. So 1, 3, 6. And then I think we visit 10 from 3 because 6 might not be connected to any other. Okay. Anyway, so the main thing this is doing is, okay, there we go. So 1, 3, 10, 7, 6. 1, 3, 10, 7, 6. That's the traversal that we would expect. Because it's pre-order, it visits the current node, then it visits the first neighbor. In this case, that was 3. It visits 3 and it visits the first neighbor. In this case, it was 10. It visits 10, it visits the next first neighbor, which is 7, and then it visits 7, and then it visits the first neighbor, which is 10. So this pre-order traversal is not breadth first because we visit 6 in the very end, even though it is a neighbor of 1, which is where we started. But yes, that's another type of traversal that we can do over a graph, and this is its implementation. The last thing to cover for today in this topic is the nearest neighbor problem. So you may have already encountered this either in machine learning or statistical methods, but the problem of the nearest neighbor problem is the idea that you have some type of data set where you have a bunch of points. It could be in 2D space, it could be in 3D space, it could be in 1D space as well. But the idea is you find a point, or you're given a point, and you want to find the nearest neighbor to this point. So you would check the Euclidean distance of this point, the Euclidean distance of this point, all of the points, and you would check whichever point has the lowest distance to the point that you're interested in. That would be your nearest neighbor. In this case, this might be the nearest neighbor. Okay, so K nearest neighbors regression or score matching are both examples of nearest neighbor problems. But the issue is in K-dimensional space, we would need to conduct a linear search through all the points. So the run time will be K times N, O of K times N. The reason we have two variables is because if we're working in high dimensional spaces, let's say we have 1,000 different dimensions for our data points, and we have 10 data points, then k is the larger factor here. So we do have to consider that number of dimensions as well as the number of points when calculating O of the nearest neighbor problem, big O of O is nearest neighbor. So there's a question, can we do better than O of K of N? And the answer is yes, if we use something called KD trees. So KD trees is short for K-dimensional trees. And note that the K here is different than the K in KNN, which is K nearest neighbors. But the KD tree has a couple of properties that allow it to work very well with the nearest neighbor problem. I'll first read the kind of the definition, and then I'll show an example which should clear it up a bit as well. So a KD tree is a binary tree where each node represents an axis-aligned hyperrectangle in k-dimensional space. And a hyperrectangle is just a rectangle in hyperdimensions. So the nodes in the left subtree have coordinates less than the splitting dimensions of the current node, while the nodes in the right subtree have coordinates greater than the splitting dimension. And at each level, a specific dimension is chosen to split the data, and the choice of dimension alternates as we traverse down the tree, and each leaf represents a single point in k-dimensional space. So let's draw this out, and hopefully that will make it a bit more clear. So let's first just draw 4 points in our space, and we will be using a two-dimensional space, but this would work with 3 dimensions as well. So let's say that this is stored at 1, 4 in Euclidean space. This, let's say, is stored at 3, 1. Let's say this is at 4, 3. And we'll say this is at 6, 2. So if we were to store this data in a KD tree, the first step is to identify where we want to split this space up. In which dimension we want to split this, divide this space, and at what value. So we generally want to try and divide it as evenly as possible. So what we can say is we can split based off of x equals, let's say, 2. So this is x equals 2. Sorry, this is x equals 3.5. So we say x is equal to 3.5, and we split our data in half this way. So the root of our tree in this case would be x equals 3.5. All of the data points that are less than x is equal to 3.5, so that includes these two, would fall to the left subtree, and all of the data points greater than x equals 3.5 would fall in the right subtree. So this goes in the left, and this goes in the right. And so that we just did this kind of step. So each node represents an axis-aligned hyperrectangle in k-dimensional space. So this is our hyperrectangle for the left subtree, and here's our right hyperrectangle, and the dimension has been split. We just covered this as well. So nodes in the left subtree have coordinates less than the splitting dimension, right have greater than. Then at each level of the tree, a specific dimension is chosen to split the data, and the choice of dimension alternates as we traverse down the tree. So that means we just split on y. In this next level, we just split on x. So now on the next level, we would split on y. So for the left subtree, it would make sense to split at, let's say, 2, because 2 divides our data in half perfectly. So we can say y equals 2. And on the right subtree, we could say that we split the data up on y equals 2.5, because that also splits our data up evenly. So this is our next hyperrectangle. This is our hyperrectangle. This is on the left subtree, our hyperrectangle. This is our right left subtree's other hyperrectangle. So we would say here y equals 2.5. And then the last point is saying each leaf represents a single point in k dimensions. So now each hyperrectangle that we've drawn contains a single leaf node. So we can now say the value less than y equals 2 in this subtree is um, 3 comma 1. And the point that is greater than y equals 2 in this subtree is 1 comma 4. And similarly on this side, the value less than is 6 comma 2 and greater than is 4 comma 3. Okay, so now we've stored all of our data points in this tree, and we can now sorry, there's an alarm going on back in the building. Give me just a second. Okay, I'm not sure if it will stop in a reasonable amount of time. My question is it very loud? Are you able to hear the beeping, the alarm? Okay, I think in that case, Zoom is filtering it out. Yeah. Okay, perfect. Um, okay, that's amazing. Um, so just one second. Yeah. So now that we've added all of the points to our leaf nodes, what we can now do is access nodes fairly easily based off of based off of the dimensions. So if we want to find any data point in this tree, we can basically just check on what basis the tree is being split on and basically come down to where we're looking for the data. So the benefit here is that KD trees can find values within certain ranges very quickly, not just a specific point. So if I want to find all of the values with x less than 3.5, that's a fairly trivial example, but if we wanted to do that, we could just look at this entire subtree. If we want to look at, for example, values less than y equals 2.5, then we would go down both of these branches, and then we would, for the right branch, only look at the left subtree because we're looking at less than 2.5. And on the left subtree, we would actually look at both branches because y less than 2.5 can occur on both sides. But moving further down, we could eventually split on that as well. So KD trees allow you to find values within certain ranges very quickly. This is used in geographic information system queries. So where you're storing coordinates of things. If you store it in the KD tree, you can find stuff within ranges fairly quickly. Similar to KNN algorithms, computer graphics such as ray tracing, all use this type of data structure. One issue that occurs with KD trees is in very high dimensional spaces, trees can become imbalanced. The reason is something called the curse of high dimensionality. We won't cover it too much in this course, but I think it will come up in machine learning, in the machine learning module. Okay, are there any questions about this before we move on to today's topic? Okay, if there's no questions about KD trees, we'll move on to slope code. So the idea behind this lecture or this notebook is sometimes you have algorithms that are simply too slow and you can't optimize the algorithm further, so you need to find other ways to get your code to run quickly. Okay. So there's a couple of techniques we'll look at. We'll start with caching, memoization, and vectorization. We'll then look at parallel computing, and then I'll talk a little bit about the idea of faster implementation versus faster algorithms. The kind of the example I'll start with for motivating this work is, let's say we have a step in our algorithm that takes, let's say 0.0001 seconds. So this is our algorithm. It takes 0.0001 seconds um, for our algorithm. Um, I'm sorry, it's just the alarm is very loud, so it's hard to talk over it. Um, but yeah, so we have an algorithm. It takes 0.0001 seconds. And let's say our data set has a size of 1 million. So if our algorithm is O of n, then this will take, let's just do the math, 0.001 times 1 million. It'll take 100 seconds. So it'll take 100 seconds, which isn't terrible. Um, it's kind of, it's, um, it'll take 2 minutes roughly. If you have to run it occasionally, you're fine with waiting 2 minutes. But if our algorithm was O of n squared, then this would take, fire alarm has been activated on the sixth floor of the building, and it. Okay. I don't think I have to evacuate as of now, so um, yeah, let's continue. So if it takes 100 seconds for an algorithm of n O of n, then for an algorithm O of n squared, it will take 10,000 seconds. 10,000 seconds, which I think is roughly 2 to 3 hours. So this is kind of highlighting that n squared is something we typically want to avoid, but sometimes, sometimes if you're able to cut this down from 3 hours down to, let's say, 5 minutes, that's kind of, that's something that you can work with a bit easier. But the issue is that you can't reduce your basic steps of your algorithm anymore, and you don't have a better algorithm either. So today's kind of lecture, or today's topic is going to cover techniques where we can kind of make last ditch efforts in order to improve our runtime. So the first technique is called caching. Caching refers to storing things for later use. You've probably heard of the term. Our browsers use it to temporarily download page details on our local disk. And the benefit is it's faster and it reduces the load on your server. Other examples include 3D rendering and saving common database queries. So I'll explain this example a little bit more. So let's say you have a computer and you want to load, let's just say google.com. Google's not the greatest example because it's a very popular website. But let's say this is the early days of the internet and you needed to retrieve Google from Google servers, which let's say are in California. So being in Toronto, we would have to travel maybe like 5,000, 6,000 kilometers in order to retrieve this page in the early days of Google. So the way caching would work is you do make that request the first time. And let's say this takes, I don't know, let's just say 10 seconds. On subsequent calls, so on the next call, rather than going all the way back to California, what you could do is just read it from your disk because you've cached it locally. So you save that HTML page on your computer, and chances are that Google hasn't updated its website, so you can make that request again. Just give me 1 second. Okay. Um, so I think I do actually have to evacuate the building, so just give me like 3 minutes. I'll just go downstairs and I think I can continue the lesson from there. Just give me 2, 3 minutes. Thanks. Okay, I think I don't actually have to evacuate. Okay, so we should be fine for now. Okay, and sorry about that. Yeah, so caching with caching, you do have to eat the cost of the computation at least once in order to actually get the data. But once you have the data, you can save it to your local device, so to your hard drive or potentially to RAM. And then the benefit is if you need it again, you can just load it from RAM rather than having to calculate it again. So caching usually takes space in exchange for faster run times. So in this case, where we're loading Google, let's say Google has a web page of 10 kilobytes. So rather than having to retrieve that data again, you just save 10 kilobytes. You use up 10 kilobytes in order to store the page, and you don't have to do that computation again. In the case for machine learning, you can sometimes do caching if you've collected a big data set and you're calculating features on that data set. So once you've collected your big data set, let's say it's like 300 gigabytes, and you want to calculate features on this, but calculating features on this takes days, let's say. What you can do is write your algorithm, calculate the feature set, and then let's say the feature set is only 10 gigabytes. So you can save that 10 gigabytes to your drive after calculating it. And then if you ever do need it again, you can just read it from the drive, which might take a couple of seconds or a couple of minutes. And it's much faster than calculating it again, which might take days. So that's another example of caching that you might see in machine learning. There's a question for processing. Would it be possible to leverage the computer GPUs for the code processing? I know you can do it for TensorFlow, but what about the rest of the code? That's a good question. So, yes, with TensorFlow, machine learning, and sometimes other libraries, you can leverage your GPU. In the case for general code, it is harder. It's generally, I don't think it's generally done. The reason is GPUs, the reason they're so quick is because they have lots of separate cores. So whereas your computer might have 8 cores or 16 cores, sometimes 4 cores, a GPU has cores in the thousands. And so the way TensorFlow and other GPU-enabled libraries are implemented, they're able to break down problems into thousands and millions of independent calculations. And so what you're able to do is split up your work into millions of different pieces and then send those out all to your thousands of cores in your GPU. And have kind of the results come back to you very quickly because you have thousands of different workers doing the same, doing the operations that you want. In the case for code, like your actual lines of code, because there's no easy way to split lines of code up in independent ways, where one line of code doesn't depend on the other. Since there isn't that type of relationship, you can't really send it to the GPU and have it compute there. But we will talk about parallelism in just a little bit, and then we'll see what we can do. So we just looked at caching. There's a type of caching called memoization, which refers to storing results of a function call for later use. So it's a specific type of caching, and um, it's useful for methods with a lot of repeated computations. For instance, in our recursive function, the Fibonacci number function, we had lots of calls to the lower Fibonacci problems. And then we would kind of use those in order to calculate the bigger ones. So for instance, when we did Fibonacci 5, we would need to calculate Fibonacci 3 2 times. We would need to calculate Fibonacci 2 2 times, maybe even more than 2 times, and so on. We had lots of different lots of repeated calls with the same number. So memoization kind of takes advantage of that. Before I jump into actually more details on memoization, I'll just go over caching once more. So caching is the idea that you have to do a calculation, but the calculation takes a lot of time. So let's say we're adding numbers from 0 to 100. So the numbers from 0 to 100 equal something like, let's just say it's 55,000. Something like this, or 5,500. Um, for us, let's say this took, in order to enter into our calculator, it took 2 minutes. Now, if we were doing caching in real life, the way this would work is we would just make a note saying that 0 all the way to 100 added up equals 5,500. Now, if anyone asks us again what the sum is from 0 to 100, without having to do the calculation again, we can just look at our notes and say that it's 5,500. In computers, it's the same concept. We have functions and we give it data and we get output. We give it input, we get output. And this can take time. And let's say this takes 2 minutes as well. Rather than having to wait 2 minutes um, we for every time we call this function, instead we save the fact that this input gives this output for this function. And so whenever we see this scenario again where we have the same input to the same we have the same input with the same function, we can just read from our disk or read from our computer the stored output that we've noted down. Memoization specifically is with function calls. Caching is a wider topic where we could cache database queries, we could cache web pages. Memoization is caching, but specifically with function inputs and outputs. So given an input, you save the output. So since we store the results, each function call is only made once, making the time complexity of the Fibonacci function much better than big O of 2 to the power of n because it's actually O of n. Memoization can also avoid the maximum recursion depth because the call stack can be smaller as well. So in the case for Fibonacci, if we recall before, we had Fibonacci 5, which made calls to Fibonacci 4 and 3, which made calls to 3 and 2, which made calls to 2 and 1, which made calls to 1 and 0. And we had this tree of execution. So it's 2 and 1. And this is 1 and 0. So we had this tree of execution. But with memoization, the benefit is if we calculate a certain input once, we don't have to do it again. So in this case, if we start with Fibonacci 5, we haven't calculated Fibonacci 5 before, so we have to do the calculation. So we go to 4. We haven't calculated 4 before, so we do the calculation, which means we call Fibonacci on 3. We then call Fibonacci on 2. Then we call Fibonacci on 1. So once we actually return 1, we save the fact that 1 returns 1. And when we calculate 0, we save the fact that 0 also returns 1. But these two function calls have now returned. And so now we've calculated 2, which is 2. Sorry, I think I'm off by 1. So this would technically be 0, and this would be 1. So 0 returns 0, 1 returns 1. 2 adds these two numbers up, which is 1. And we also save the fact that Fibonacci 2 returns 1. Then we go up and we see that we need to calculate Fibonacci 2, which we've already calculated as 1, so we don't have to do that. And we don't even go down this branch because we see that we need to calculate Fibonacci 1 and we've stored the value of 1. So we're able to add 1 plus 1, which is 2. We get the value of 2, and we store this in our memoization as well. So now we've returned 2 over here. 4 now needs to calculate 2 plus the Fibonacci of 2, which we've also stored right here. So we will add these two to the up and we will return 3. Now Fibonacci 4 returns 3 to Fibonacci 5. Fibonacci 5 needs to calculate Fibonacci 3, which it can do by just reading our memoized value. So then we get 3 and 2, which we add up and get 5. So the benefit, so 1 second. Okay, the fire alarms situation has been resolved. Okay, so yes, the benefit of memoization is that we don't have to do the traversal of the full tree. We just have to do the calculations for each n, for each value of n from 0 to n. And everything else we can just read the values that we've saved. One implementation of this, actually, this is our original Fibonacci sequence. And if we calculate Fibonacci 40, it takes roughly 30 seconds to calculate. I've done this before, so I don't want to spend the 30 seconds here right now. But calculating Fibonacci 40, actually, let me just run it. It'll take 30 seconds to calculate that number. On the other hand, we have this same function. The only difference is we are now caching the results of our function. So let me actually call this Fibonacci. Actually, it's fine. Okay, so the way that we're caching the results is we first store in a dictionary. So we call dictionaries are O of 1. We stored in a dictionary the input and output that we expect from the function call. So to begin with, we'll just put in our base cases, which is that Fibonacci 0 should return 0 and Fibonacci 1 should return 1. And then in our actual function, what we do is rather than making our base case, the base case 0 or 1, we essentially just check if our input has been calculated before, and if it is, then return the value. So if n is inside cache, if the input is inside our cache already, then return the value associated with that input, return the output for that input. Otherwise, if we haven't already calculated it, then do the calculation, so make the recursive calls, but save it in our cache and then return the value from our cache. So that on subsequent calls, if we need to do the same calculation, we can then just read it directly from cache. So to begin with, this only contains values 0 through 1, but when we actually calculate a number like 40, this will get populated with all of the values from 0 to 40 and their outputs as well. So let's try running this. And also note the runtime. It's pretty much instant. Whereas this did take 30 seconds to run roughly, this was almost instant. And if we look at our cache, we've stored all of the results from 0 all the way to 40. And the way we were able to do this is rather than having to traverse that entire tree that I drew out, we were able to just refer to the previous values that were calculated, and we were able to then use those to calculate the next one. And the benefit here is even with very, very, very big values like 3,000, this is calculated almost instantly. If I was able, if I was to do, I was able to, if I was to do 3,000, like this, I think it would probably never execute. I think that just scales so fast that it will never complete. Okay, so for base cases, we replace calling fib0 and fib1 by getting the values from the dictionary. And this dictionary is all of our results. So this was a very specific implementation for Fibonacci, but in practice, we don't tend to use dictionaries. Instead, we rely on libraries who have implemented this in better ways, or not necessarily more efficient ways, but easier to use ways. So rather than having to modify our function and kind of think about the logic of managing our cache, there are functions which just let us add a decorator to our function, and it will handle everything else. So so if we use the functools library, that's the one that contains the memoization that we use. It's also included in our standard library, so we don't need to use pip to install it. We can use something called the cache decorator. But the downside to the cache decorator is that it can grow to very big sizes. So instead we use the LRU cache and specify a maximum size. The LRU stands for least recently used, and it stores n computations. Our alternative is that we can also use something called joblib to store the memoized results in a file. So that is a key distinction that I want to make. The LRU cache stores in memory, in RAM. So that means if you restart your kernel, your caches will be gone. Joblib, on the other hand, stores to your drive, so stores to your directory, to your folders. So you would have to specify a path to store it in. But then if you close your kernel or you close your session and come back to it, your caches will still remain. So that's the difference between these two different libraries. But yeah, let's take a look here. So this is our original Fibonacci function. If we start from here, this is our original Fibonacci function that we implemented before, but the only change is we add this decorator. I'm using the word decorator. A decorator is just it's almost a function call. It's something that you add to a function call before a function, sorry, a function definition. It's something you add before a function definition, and it gives it some property or some ability. In this case, it will cache any outputs of this function, and if the input matches to previous calls, it will give you the same output. So if we run this line, it will also work. Sorry, so so this hits maximum recursion, but if we do it with 300, we can solve this fairly quickly. So there's probably a question that comes to mind, which is with least recently used, how are we able to only store 3 values and still calculate over 300 values in our recursion? So the way this works is that we're saving the 3 most recently used outputs. So in our case for 5, for actually let's go a bit higher. Let's say 15, 14, and 13. And let me just add one more layer. So that's 13 and 12. So the way that least recently used works is when we calculate, let's say, the leaf nodes for this tree, we first store 1, 2, and 3. But then when we need to calculate 3, we only use 2 and 1. So 0 kind of starts becoming stale because it wasn't really needed in order to calculate 3. And so when we calculate 3, we end up replacing 0. And so now in our least recently used cache, we have the values for the outputs for 3, the outputs for 2, and the outputs for 1. And the benefit is when we need to calculate 4, we only need 3 and 2, so we're able to overwrite 1. So using this, we're able to essentially um, store only 3 outputs, and that'll let us calculate as high as we need to. Yeah. And the benefit is it also takes up very little space since it's only storing the outputs for 3 values. Okay, and let me just see. Okay. Yeah, so I mentioned the joblib library. The one that I personally use is called Cachemal. It works very similar. You just similar to this, where you just add a decorator called cacheable, and then you just I think you just add the decorator and potentially the file format that you want to save it in, and it will do the same thing except store to drive, store to disk. This I think is just an example based off of a question that was asked in the past. Okay. And yeah, so that is caching. It's a fairly powerful technique, and it lets you. It doesn't necessarily doesn't necessarily save you time in the sense that you do need to make that call at least once in the beginning. But if you have a function where you're making repeated calls and there's lots of growth in that sense, sorry, there's lots of kind of time complexity in that sense, then caching can also reduce your runtime in the first call, like we saw with Fibonacci. There's a question, are these cache libraries be used for distribution systems too, distributed systems? Um, I think absolutely you could use them. So with distributed systems, you have jobs running on multiple different machines. Typically, these machines don't have a shared file system. So I don't think the cache would live between all of your distributed nodes, because then accessing those caches might cause contention or cause timing issues. So waiting for the cache to be available would cause you to slow down. But potentially you could create separate caches on each distributed node. And in that sense, if you have the same input to your distributed nodes, um, you could save time there as well. Um, yeah, there are other ways to cache data in distributed calculations. Okay. Yeah, so apparently there are ways to cache data in distributed calculations. I'm not familiar with them. Intuitively, the one thing that does come to mind is the head node, the one that's allocating all the different work, could start caching the results from workers and only make distributed calls if the data hasn't been calculated before. But yeah, I haven't worked too much with distributed systems, so I don't know what the what the latest technology there is right now. Okay. Um, yeah, moving on to vectorization. So vectorization is a technique of implementing array operations without for loops. We use functions defined by various modules that are highly optimized for specific problems. For example, NumPy provides a lot of functions that are vectorized and are faster than for loops, such as adding array addition, subtraction, multiplication, division by a scalar, summing an array, or finding the max or minimum of an array. Another example is machine learning processes that are iterative, like gradient descent. All of these examples use vectorization in order to do array-based operations quickly. The reason vectorized operations work comes down to the programming language here. So Python is something called an interpreted language. What that means is when we write our code, so let's say this is our code, when we want to run it, we give this code to Python directly. So this is Python, and what Python does is it looks at the first line and it runs it. It doesn't look at any of the other lines. It doesn't look at the second, third, fourth line. It looks just at the first line and it runs it. The benefit of this is that it's fairly easier to work with in some cases, like with these notebooks. I can just write a single line and I can send it to Python, and Python is happy to run it without knowing what comes next. But one of the downsides is that it doesn't know what's coming next, and so it has to basically just do what it's told. It can't be clever about finding shortcuts or doing stuff quicker because it knows what's going on. The other type of programming language is something called a compiled programming language. So with compiled programming languages, what you do is you write your code, the same as interpreted languages, except you then have an intermediate step where you have to compile your code. So that means you send your code to something called a compiler, for example, GCC for C, um, GCC, let's say this is C code. You send your code to GCC, and this outputs an executable. So then you have something, let's call it .exe, but normally it's just, it doesn't have an extension in Linux, but let's say you have an executable. Then what you can do is run this executable and your program will run. So this is how you run your code. The benefit comes in the compilation. When you give your code to GCC, GCC is able to look at your entire code, your entire file, and it's able to see what you're doing and understand the full context of your program. And so if it's seeing that you want to do some type of array operation, like let's say you're adding, let's say you're adding zeros to your entire array. If this was given to C, C might be able to make the optimization of seeing you're adding zeros to your array, but that doesn't actually change the value. So I'm just going to not do it. That's just an unnecessary operation. On the other hand, Python, when you tell Python to add a bunch of zeros to your array, it doesn't know what you're going to do next. So it will just do it, trusting that what you're doing makes sense. Now, adding zeros isn't the greatest example because that's just a single operation that you can look at and tell that it's not doing anything. But let's say that there's 3 lines of code, and in these 3 lines of code, you're doing 3 steps that could possibly be done in a single step. So GCC is able to actually see all 3 steps and identify that this could just be done in a single step and is able to then do that in a single step. So that's the benefit of having a compiled language is it's able to make optimizations. And so when NumPy functions like addition, sum, or max, min are implemented in C, it's able to actually take advantage of those optimizations and do operations more quickly. Another benefit is because it's able to make those optimizations and it knows the full context of the operation that's happening. It's also able to do some stuff in parallel. Um, it's able to kind of do multiple actions at once. With Python, it runs into a similar issue of that we talked about with optimizations, where it doesn't know the full context of what you're trying to do, and so it's not able to make those optimizations as easily. If you're iterating over a full loop, um, yeah, if you're iterating over a list of elements, Python is most likely going to just do that one by one because it doesn't really know what's going on in the full context of the program. So that's why the main takeaway from this kind of shorter section is that if you have the option of using NumPy, Pandas, or some other vectorized library to do an operation, you should opt to do it rather than using Python native lists. Python does give you the benefit of having more flexibility when writing your code, but in terms of actually running your code, it is fairly slow. So NumPy, Pandas, and these types of libraries allow you to also use the benefit of compiled languages in your program. The other benefit, or the other kind of way to speed up your code is called parallelization. So that falls into parallel computing. And we will start with this example right here. So if we look at both of these programs, sorry, my computer might be having a little bit of trouble loading. Okay, so if we look at, if we look at both of these codes right here, what are the runtimes of each? So looking at this, we can see that because it is using caching, it's only going to need to make all the calculations once. So the runtime of this, as we discussed earlier today, is O of n. And let's also look at this function. Though this function takes in a number n and a number x. And what it first does is an array of size n where all of the values are 0. So it creates, and this we know is O of n because it just needs to create n elements in an array. So that is O of n. We then iterate over n. So this is again O of n. And then we add 1 to the value that is stored in our y using x sub I. So I is actually a list. X is actually a list. But we know that array accesses are O of 1, so this is O of 1. So overall, this function also has a runtime of O of n, big O of n. So both of these functions have the same runtime. This is O of n, this is O of n. But there is a key distinction between them that allows for parallelization of this function. And that distinction is that the operation for each element in this function, in the second function, is independent of the calculation for every other element. So we're adding x sub I plus 1 and saving it in y sub I. But that operation didn't depend on x of I plus 1 or x minus 1. It only cared about the ith element. So in this array with n elements, each element was calculated without relying on any other element. In the case for Fibonacci, that's not the case. When we want to calculate Fibonacci of 10, we first needed to calculate Fibonacci of 9 and Fibonacci of 8. So this reliance prevents the use of parallelization. But if you have a bunch of independent operations, like the case for this function, you are able to use parallelization. Parallelization as a concept is the idea of doing multiple things at once. So in your computer, you have a processor, and your processor has multiple cores, and within cores, you also have threads of execution. So let's say this is our processor. It's a quad-core processor, meaning these are 4 different cores, and then each core has a thread as well, but we won't go into threads just yet. So high level, we can say that this processor can do 4 things at a single time. 4 things at once. So what we could do in parallelization is tell core 1 to calculate this value, tell core 2 to calculate this value, 3 to calculate this one, and 4 to calculate this one. And when core 1 is done, then to calculate the next one, so on and so on. So basically, you're splitting up the work into smaller chunks and then sending those out to your cores. And because they're independent pieces of work, the cores don't need to talk or communicate between each other because all their work can be done independently. GPUs operate on a similar structure where you have these cores doing independent pieces of work. But the operations that GPUs can do are very, very specific and optimized. So GPUs do matrix operations well. They do some types of calculations well, but they don't do other things as well. They don't do other things as well. So if we're talking about general programming, and the wanting to use parallelization for that, the only requirement is that it needs to be independent, and you're able to then run it on multiple cores. So let's go over this. So both are O of n, but the second code chunk can be done in parallel because the n computations are independent. Fibonacci depends on the previous two values. The requirement for code to be parallelized and vectorized is similar, but not the same. There's a library Numba, which can help you parallelize your code. But note that parallel means that the processes take place on one machine, whereas distributed means that computation is shared across many machines. And you can also use parallelization and distribution um, in order to um, improve runtime even more. So this is the kind of the last concept before we'll take a break. Um, but yeah, um, there's two ways that we can speed up our code. We can use a faster algorithm. We can look at techniques like dynamic programming, um, or we can um, or we can approach the problem in a different technique, which will result in a lower runtime, like O of n rather than O of n squared. That's the idea of using a faster algorithm. But once you've settled on your algorithm, you can then explore using a faster implementation, which is what we discussed today, such as vectorization or loops. And this will then improve your performance even more. And it's useful to think about these separately when developing a program, but then combining them in order to create a super fast approach. So, um, that's kind of the lesson on this topic. We'll take a 10-minute break, and after we come back, I'll go over a code example that came up in my research, and I'll kind of show how I used all of these techniques in combination in order to improve my runtime. After that, we will do a shorter lesson on the idea of bottlenecks. And that's going to be even more practical. It's going to be kind of a different perspective, but will also help you improve your programs and um, programming environments. But let's first take a 10-minute break. We'll come back at 7:19, and then we'll look at our code example. Let me see if there's a question. Can you quickly go over assignment 2 while the break is happening? Sure. So let's officially start our break. We'll come back at 7:20 just because I'll also take a little bit of time in explaining assignment 2. But if you'd like to step away, feel free. I'll just explain assignment 2 um, briefly. Okay, so assignment 2, you have if you've submitted assignment 1, most likely you've received a message from me giving you a partner for assignment 2. What you will do is there's 4 parts to the assignment. Part 1 is going to look very similar to assignment 1, where you will figure out the output for your from this function. So you'll put your first name here, you'll get a number, and that's the question that you need to work on. It will say either 1, 2, or 3. So that will tell you whether you need to do question 1, question 2, or question 3. Once you complete complete the question, you can then move on to part 2, which is independent of part 1. So it doesn't depend on part 1. Part 1 is just an exercise. In part 2, you will go to the Slack message that I sent you, and you'll open up your partner's pull request. If you don't see a pull request, it's possible that the pull request was closed. So you would need to look at the close tab, but your partner should have a pull request somewhere there. And you will open up their code, look at their submission for assignment one, and understand their solution. So specifically, they answered one of three questions. You'll look at their solution, and the question that they would have completed will be different than the one that you completed for assignment one. So you'll be looking at a different question. In part two, all you have to do is review your partner's submission. You don't actually have to do anything in terms of coding or reviewing. That comes in part three. And in part three, you're going to perform a code review of your partner's assignment one by answering the questions below. So if we look in part three, okay, I'll repeat that in just a second. But if you look in part three, you have all of these questions. You need to answer these in the context of your partner's assignment one. And so you will answer all of these all the way down to here. And then in part four, you will write a reflection, commenting on your experience, doing a code review of your partner's assignment. What I said about part two was all you have to do in part two is review your partner's code. So you will just read through it, make sure you understand it and how it works. There's nothing you have to submit for part two. All of that is done in part three. Does that clear up assignment two? Are there any questions?
Hi.
Yes.
Hello. So the assignment you say the part two has something I need to paraphrase what my partner submitted as part of assignment one.
You have to do that in part three, right here.
Okay.
Um,
Paraphrase, I mean, entirely like paraphrase the problem in your, I mean, actually, I'm repeating the work that I had done as part of my assignment one. In the
sorry.
part three, I'm gonna do the one that I've done for my assignment, for my partner's assignment.
Yes. So let's take a look. So let's say this is you, this is your partner. You did assignment one, and let's
Hmm.
say you answered question two. Your
Hmm.
partner in assignment one would have either answered question one or three. So let's say
Three. Yeah.
they would not have done two. So you
Yeah.
will not get
Okay.
the same question. Then in your assignment two, you will be looking at their solution to question three and
Yeah.
answering all of these questions.
Yeah. Okay.
Partner will be doing the opposite. So they will be looking at your assignment to your
Hmm.
question two and answering the questions for
And
them.
then part three. But in part two, what am I doing then?
In part two, you are just opening up your partner's question
Hmm.
and reading it. So this is more of just you working through reading your
Okay.
assignment.
Okay. Just writing that what he had done or he or she, whatever has done.
You don't have to
Part of.
write anything for part two.
Okay. Yeah.
Nothing needs to be done for part two in terms of this notebook. It's
Okay.
just you have to read it.
I have to read it. Not that I have to submit anything, right?
Correct.
All right. So then that's gone. Part two and part three is done. And how about the part four? Is that
Part
part
four
four?
is a reflection.
Okay. Well, give an example like how he did. Like suppose he has written for part three. So sorry, he has written for question number three.
Yep.
Okay, so I'm gonna write something that how the work has been done by him. A complete reflection of mine.
So this is more of a self-reflection. So how did you how was the process for reviewing the code?
Okay.
Did you struggle understanding something? Did you feel like something could be improved? It's more of a reflection. Self,
Okay.
yeah.
So it has to be within 200 words.
Yeah. It's not a strict limit, but that's roughly the length that it should be.
Mhm. Thank you.
Yeah, no
That's good.
problem. There's a question in the chat for part one. We are completing the code for the respective questions we are assigned. Yes. So you're going to put your name right here where it says your first name here. It's going to output either one, two, or three, and that's the only question you have to solve. It's going to be one of the three. And there's also a raised hand.
Yeah, thank you. Part 3 says to create a Jupyter notebook as part of the instruction. So are we submitting a separate Jupyter notebook in addition to this?
No, I think this is just a bit outdated. So
Yeah, and
you
part
don't
4
have to
also says to
you don't
create
have
a
to create a
PDF.
new notebook. It's just going to be answered here.
Yeah,
Yeah.
okay. Yeah, part 4 also says to print it off as a PDF, like to export it as a PDF. So,
Okay, I'll make sure to update those two.
okay. Yeah, thanks for the clarification.
No worries. Okay, and yes, we will resume at 7:20. So we have a couple more minutes. Okay, let's get started. So, this is an example from my research. So my research is on using worn devices like smartwatches to predict exacerbations of COPD before they happen. So exacerbations are episodes in the disease where symptoms are more severe and medical intervention is typically required in order to prevent them from getting worse. If a patient is wearing a smartwatch, we're trying to figure out if we can tell if their respiratory systems are worse or their baseline. So what we did was we ran a study with ethics approval where we gave people with COPD a smartwatch and a smartphone, and the smartwatch would continuously record their heart rate, their movement, as well as their audio. So that audio component, the microphone, was the idea behind it was that we wanted to be able to capture their breathing sounds, whether their speaking patterns are changing, whether they're coughing. But because the microphone was a very sensitive modality, um, the ethics requirement was that we need to muffle any speech that occurred in the signal. So we ran a muffling algorithm, but we were allowed to extract features from unmuffled audio. So before we actually muffled it, in order and save those in our servers. So we could save extracted features on unmuffled audio, but we would have to muffle them before saving them. Before we would have to muffle the audio itself before we could save it locally. So all of the feature extraction actually happened on the smartwatch, so that we never actually had access to the unmuffled audio. But we could also use features to construct audio back, compute new features as well, and compute new features as long as we didn't listen or stored the reconstructed audio. So some features are reversible. One example of this is FFTs. They're a type of feature that you can extract from signals. And if you calculate the FFT, you can also then reconstruct the original signal from the FFT. The way FFTs high level work is they convert signals from the time domain to the frequency domain. And we were allowed to do this based off of ethics approval as long as we never actually listened to or saved the audio. And the reason we would do this is if we needed to calculate new features. So the issue that we ran into was that this was a joint study with Samsung. So half of the software was developed by us, the other half was developed by Samsung Digital Health. And so they were the ones that were computing a lot of the features. And so we were being handed FFTs as the data that was being collected. And I personally needed to figure out how to um, reverse the signal from an FFT into an actual audio signal. So in our trial, we collected 122,000 audio files. Each audio file was 2 minutes long, and yeah, so we had 122,000 FFT files. And so if I need to ever calculate a new feature that we didn't already have, I would first need to reverse the FFT, calculate the feature, and then save the feature value and discard the reversed audio. But if I opened up my CSV, my FFT, sorry, if I looked at the FFT that Samsung was giving us, this is what it looked like. This is right now a sample data, so all these zeros would just be random numbers. But this was kind of the dimensions that I was working with. And I wasn't able to actually get the implementation details for this function. So I needed to kind of figure out how to reverse this FFT on my own. So there are libraries like inverse FFT from NumPy or maybe scikit-learn that reverse FFTs, but because FFTs have so many different parameters like step size, window size, overlap, and smoothing functions, I really didn't know what we were working with. So what I ended up doing in order to reverse the FFT was I recorded my own audio sample using the smartwatch. And then I basically was just testing out different things based off of what I was seeing here in order to reverse the FFT. This process, I think, took 1 to 2 weeks, but eventually I came up with this function that was successfully reversing the FFT. So coming up with this function was a 2 week struggle of writing a function, running it on my FFT. It would output an audio, and then I would play that audio through like VLC or an audio player and listen to the audio. If it sounded normal, that means that my FFT function was working, but 99% of the time, or for 2 weeks, it was just giving me garbage. Like the audio signal was garbage. It was just random static noise. And so after 2 weeks, I finally kind of pieced it all together and I was able to run this, and the audio actually sounded legible. It sounded proper. So once I had this function working after so much time, I was very hesitant to say change it. So I was like super scared that if I just changed even one thing, it'd stop working. I would have to figure that out again. So I was happy with this function. But if I ran this, sorry, I just need to run these lines of code. I think maybe I don't have this installed. Okay, so where was I? Yeah, so I implemented this function, and as we can see over here, if I give it the FFT, it gives me an audio signal. But if I time the amount of if I look at the amount of time it takes to run for this one audio file, it's 1.4 seconds. That's not too bad on its own, but given that we have 120,000 files, and if I ever need to calculate a new feature, I would need to run this function on my entire audio data set. So if we extrapolate for the number of files that we have, it would take roughly 2 days to calculate this function. Oh, sorry, to calculate this over my entire data set. Yes, there's a raised hand.
A question regarding the 2 weeks that you kind of waited. So when you did the inverse FFT, right, over here,
Yes.
and then after you did, then you did a sample where you turned your audio into FFT, correct?
Yeah, so I did that beforehand. So I ran my audio through my smartwatch pipeline, and I got an FFT, and then I tried to reverse it using this function.
Using this function, so that was a test.
Yeah.
When you did the 2 weeks inverse, what were you trying to figure out? You're trying to figure out what are the variables and stuff so you can write this function?
Yeah, so if we actually look at this function, we have we have a complex component, we have an imaginary component, and there's a certain amount of step size and window size. If I'm trying to find it. Yeah, I think the window and step size were the default, but it was a matter of trying to figure all of these kind of parameters out, because I had very little information.
Okay, thank you.
But yeah, so looking at the fact that it would take 2 days in order to calculate any feature that I wanted, like this was the minimum amount of time, I decided it wasn't worth it. And knowing that we can optimize this in quite a few ways, I decided I'll try. So the first thing that popped out to me was I was using a for loop, and that means I'm using Python list operations, whereas I could be using NumPy. So I worked on understanding exactly how to kind of present this as a um, or sorry, how to represent this using NumPy operations, represent these operations using NumPy operations. And this was before the days of ChatGPT. I think this was in roughly 2019 or 2020. So I couldn't just ask ChatGPT to vectorize this. But after very hard thinking and kind of coming up with something, I ended up replacing that entire for loop with this one line. So I couldn't tell you exactly what I'm doing here, but it's like I'm looking at both dimensions, but in the second dimensions, I'm skipping every second value and I'm adding it up with the imaginary component, which is again every second value, but um, offset by one. So this it's a single line, but it took a lot of kind of thinking and testing in order to condense this one line down to this. But now with this function, I've gotten rid of any for loop and while loop in my function. Sorry, in my function. So this was in a way this was O of n because I'm iterating over an array versus an array. So this was sorry O of n squared. So this kind of got rid of that, and we can see it's still working the same, but now it's only taking 0.2 seconds. And if we extrapolate for our entire data set, it's now down to 6 hours from 2 days. So this was our first kind of way of optimizing our code, which was vectorization. Now, the server that I was running this program on was a fairly beefy server. It had I wrote 32, I think it actually, yeah, 32 cores. It has 32 cores and 64 threads, as well as 128 gigabytes of RAM. So if I could, because each file in this situation is independent, if I ran this in parallel, where each thread of execution was running on just a different file, then I could cut my runtime down by 64 by a factor of 64. So I ended up using the joblib library. The joblib library lets you do parallel programming. And I basically just used that with 64 threads of execution. I ran my function for all my files. I've put inside an if loop because I'm currently running on my laptop, so I don't have 64 threads, nor do I have all my files. But if I was to run this in my actual environment, it would take 6 minutes. So that's down from 6 hours to 6 minutes because we're able to use parallelism. So this is kind of what ended up happening when I was doing my when I was in the beginning of my PhD. I ended up being able to use both vectorization and parallelization to cut my runtime down from 2 days to 6 minutes. And yeah, some of it was improving the algorithm, so going for vectorization rather than for loops, but some of it was also just making better usage of my compute. Yes, there's a raised hand.
Yeah, so how did you figure out how many cores that you are going to use when you were parallelizing?
Yeah, so typically you can you should know the amount of cores that your computer has. If you don't, what you can always do is look at /etc/cpu info. Sorry, I think it's proc/cpu info. So let me just do that here. Let me try this. Okay, so on my MacBook, there isn't a CPU info, I'm guessing. Yeah, there's no this doesn't exist on MacBooks, but it does exist on Linux machines. But essentially, this file tells you how many cores and threads that you have on your computer. If you're on a Windows machine, I think if you just go to My Computer and then click Properties from My System, it should show you there as well, or in Task Manager.
So you
But
mentioned, yeah,
sorry, so this will tell you the number of cores and threads you have. Typically, you have like four. If you have 4 cores, that means you have 8 threads. This will also most likely be written in your task manager. Um, then it's kind of up to you. If you use 8 threads, if you use all your threads on your machine, then if there's any other thing running, most of those will kind of slow down or stop. It depends on the load on your machine. But if you use 8 threads and you have only 8 threads, you're going to use your entire machine.
okay.
If you're doing other work or someone else is also using the same machine, that's typically the case when you have like big servers at your company. Then you typically want to base it off of how much work is being run on the computer at that time.
Okay. And you also mentioned about using a for loop in your machine because you did this in your machine, right? So I didn't understand the part that why did you use for loop?
So the reason I initially used the for loop was because that's kind of,
No, the for loop in parallelization.
sorry, where?
The for loop when you were parallelizing the code.
Here?
Yes, yes.
This is the syntax for the parallel joblib parallel call. So the way parallel works is you kind of inside these brackets, you you tell it how many threads of execution you want, and then you have another set of brackets, and inside this you have your function call inside something called delayed. And then you have this second kind of set of brackets, and this is where your input goes. And then here you're supposed to iterate over your input. So this is very, very specific syntax used with this library. If you open up their documentation, they'll kind of explain it and tell you how to use it as well.
Okay, thank you.
Yeah, no problem. Okay, so that covers this example. And typically this is kind of the approach that you take. You first kind of come up with an implementation. If you're fine to live with this runtime, if your data set is small enough or it doesn't really matter, you can just run it once or live with the runtime. But if you know that in the future you're going to have to rely on this more, or you can't this runtime is too high, then you can look at optimizations. That can be through improving your function, or it can be making better use of the resources you have available. So with that second thought of making the best making the best usage of your resources, let's start our last topic for today, which is bottlenecks. So 1 second. Yeah. So bottlenecks is a computer science kind of concept. Well, I think it exists elsewhere as well, but in computer science, it typically refers to the slowest part of your program. So the bottleneck is the slowest part of a process that limits overall speed. The reason I kind of use more general term here, so slowest part of a process rather than a program that limits your overall speed, is because when you run a program, that program doesn't just run in isolation, it depends on a lot of other things. So it could depend on your networking speed, it could depend on your hard drive speed, it could depend on your CPU speed. And so figuring out that bottleneck is what tells you what you should focus on in order to improve, um, in order to obtain the most benefit um, from your effort, like improve the runtime the most based off of the smallest changes. So, for instance, so in this course so far, we've analyzed algorithmic bottlenecks using big O notation. So we've looked at specific lines of code, and we've identified that this specific line is what's the slowest part of our code. So this is what we should improve if we want to see better runtimes. But performance bottlenecks can arise from many sources beyond just algorithmic complexity. So, for instance, if we're training a model, then it has a high computational cost. So that is just the CPU or the GPU being not fast enough, or it's hitting, that's the part that's causing the slowest, that's taking the longest time. If we're doing feature engineering, this could be more dependent on potentially the CPU rather than the GPU, or it could be dependent on RAM or hard drives. If you're loading a lot of data, then this could depend on your hard drive speeds or your SSD speeds. And if you're downloading a lot of data, then it could depend on your networking speeds, and you could experience delays in fetching remote data. So the key takeaway here is that finding and addressing bottlenecks is critical for optimizing performance. If it is an algorithmic bottleneck, then focusing on the big O of your algorithm is kind of where you should spend your energy. But sometimes your bottlenecks can be occurring somewhere else. So let's take a look. So bottlenecks aren't always due to poor algorithms. They can exist elsewhere as well. For instance, external factors like hardware, network latency, or I/O constraints often slow down programs. For instance, in a real-world scenario, a deep learning model may run efficiently on a GPU, but if training data is stored on a slow external drive, then training will still be slow. So you could buy the best GPU in the world, but if your data is stored on, let's say, hard drives and your data is very big, then if you're loading the data from your hard drives, the training will still be slow. So down here is kind of how a computer is structured and what typically it connects to. So the first thing I want to focus on is the CPU cache and RAM. So this is the CPU. The CPU reads data directly from memory, and anything that it uses more often, it stores in cache. So the typical speeds that we see from cache, so whether that's L1, L2, or L3 cache, which all exist inside the CPU, is close to 100 gigabytes per second. The size of cache is actually very small, so we're never storing gigabytes in cache, but it can read very, very quickly. It can read data very, very quickly. On the other hand, RAM is slower than cache, but it is still very, very fast. So RAM typically has read speeds between 20 to 100 gigabytes per second. And these two locations, cache and RAM, are typically the fastest place to store your data. When you create variables in Python, those are being stored in memory and potentially cache as well. You don't manually manage cache. The CPU does that on its own. But when you create variables or read stuff from disk, you're essentially storing it in memory. And typically, if the data is in memory, it's usually not a bottleneck. Because the CPU is reading from memory directly, that read speed is generally not that much of an issue. So you're most likely not going to encounter any bottlenecks if you're storing your data if you have your data already in memory. But if it doesn't fit, it needs to be stored in on the disk called storage, and that's going to slow down performance just a bit. So memory access is rarely the bottleneck in processes unless you're working with massive data sets. So if you, for instance, have if you have 32 gigabytes of RAM on your machine, but your data set is 1 terabyte, then it's not feasible to store your entire data set on your in your RAM. So you're going to have to chunk it up and load it in from your storage into your memory, reading potentially 20 gigabytes at a time or 30 gigabytes at a time. So that reading from storage could be a bottleneck, but that reading from memory into CPU most likely won't be. The next tier, so memory is very quick. Storage is typically larger than RAM or memory, but it is slower. In the case for storage, you do actually have a couple of different types of storage. You have hard drives, which are typically the slowest, but contain the most amount of storage capacity. The read speeds for hard drives are typically around 100 megabytes per second, um, give or take a bit, depending on how old or how new the drive is. On the other hand, so we have hard drives, and then the other kind of counterpart to that are SSDs, and SSDs do come in different formats as well. SATA SSDs have read-write speeds of roughly 500 megabytes per second, and NVMe SSDs have typically read-write speeds of 5 gigabytes per second or 5,000 megabytes per second. So if you're working in a machine and you know that you need to read lots of data from your storage, and you know that that's going to be a bottleneck, then you could always consider upgrading your storage solution. So if you have a hard drive, you could consider getting either an SSD that works over the SATA port, or if you want even faster read speeds, you could look at an SSD that connects directly to your NVMe slots on your motherboard. So you can upgrade your hard drive or your storage solution in order to improve read speeds. So if your data doesn't fit in RAM, then frequent disk access is slow performance. And the solution to this is either upgrade your storage speeds or optimize your data formats as well. So you can also use data formats that are optimized for reading. So that means that they take less space on your storage. But the downside is then you need to convert that into a readable format potentially, and that will take some computational cost. So there's probably a trade-off there as well, but that is an option. Another option, as I mentioned, is upgrade storage, but the last is also fairly interesting. which is leverage memory mapped files. So this doesn't work if your RAM is too small, but if you need to store your data in storage and then need to load it into RAM for whatever reason, what you can actually do is create something called a RAM disk. So a RAM disk is when you have RAM, let's say um, you have 32 gigabytes of RAM. Actually, let's say you decide to upgrade your RAM and you get 128 gigabytes of RAM. A RAM disk is where you portion off a section of your RAM. So let's say we decide to portion off 32 gigabytes of RAM and leave the remaining 96 as our normal RAM. What we can say is that this portion called 32 is our RAM disk. What a RAM disk is it's a portion of RAM that acts as storage. So in your file system, you can probably have some directory. Let's just say you're in your home, and then you create a new directory here called RAM disk. So any file that you store in this directory will look like it's a file on your hard drive, but this directory is specifically being stored on your RAM. And so reading files from this directory will have RAM speeds, which are very, very quick. 100 megabytes per second, I think I had in the previous slide, 20 to 100. So you can leverage RAM disks if you have constraints like you need to store them in files and you need to work with files. This isn't typically a solution to overcome issues where your data set doesn't fit in RAM, because you do need to allocate RAM for it. But if you need to work with files, this is a solution that you can use. Typically, disk I/O can be a major bottleneck because in the context of working with CPUs, cache, and memory, storage is a magnitude slower. It's potentially 10 times to 100 times slower. So if you do need to rely on storage a lot, this is going to end up being a major bottleneck, and you need to kind of figure out how you can improve your runtime or fix this bottleneck in terms of storage. Worse than storage, though, are networks. So, okay, so I'm not going to say strictly they're worse because networks have gone fairly quick at this point. With high-end servers, you can have read speeds of 10 gigabytes per second, 100 gigabytes per second, gigabits per second. But even then, working with networks can be a bottleneck as well. And in terms of in terms of networks, we do have two different types of networks. We have local networks, which means that you're kind of connected to your access point or your router, and your router is then communicating to other computers locally within the area. So for example, if this is our computer 1 and we wanted to read data from computer 2, we could have a potentially wired connection all the way to computer 2 through the network or router. It's also possible that these are connected through Wi-Fi, which would be a bit slower, but it is still a local network. On the other hand, we can also have data stored over the internet. So this could be like something stored on Amazon S3, or in the cloud or on someone else's remote server. So internet speeds are slower because they're geographically further, and rely on mostly because they're geographically slower. The actual cables and speeds of the internet are fairly fast until you get to the last node potentially. So the main thing is local networks are typically faster, internet speeds are typically slower. Some of these numbers can be outdated, or may be outdated because you might have gigabit Ethernet or 10 gigabit fiber optic lines are fairly quick. But this is still a potential source of bottlenecks. Bottlenecks with networking arise when you're fetching a lot of data from remote servers, or you're making a lot of calls to APIs. So if you're relying on these, a lot, they can end up creating a bottleneck in your program as well. Some solutions for this is download the data once and then cache it locally. You could also make batch requests instead of many small ones. So you can say, give me the next 20 files. And then when you're operating on those 20 files, you've already requested the next 20. So as you're working on the data, you're also making progress on the data that you've already received in computation. So that could also increase your runtime because you're making fewer requests and you're making progress while working on the data. You can also use compression when transferring data. So this is again trading storage space for compute. So you're going to do a little bit of extra work in order to compress your data, but then when it's actually transferring over the internet, the size of your data will be smaller. So the takeaway is try and reduce the dependence on remote data access when possible. And this is a source of bottleneck, so always try and improve your networking speeds as well. So in the case for U of T, we have like a server cluster in the lab. So all of the connections between the servers are very, very high speed. So all the servers I think have either 10 or 100 gigabit Ethernet. The networking switches for those were very expensive, but the benefit is now all of our servers, when communicating with each other or transferring our data, because we do have very big data sets, is very quick because our networking speeds are very good. Okay, so the next kind of thing that I will very strongly recommend against is relying on manual input. So I doubt you'll have this often, and sometimes it is unavoidable. But in some situations, you do have to rely on user input. So for instance, labeling a data set by hand. This is something we actually had to do as well once, or reviewing model predictions manually. So these are situations where a human needs to actually look at the data or do something and then provide input. This is incredibly slow. When we were labeling a data set by hand, it took us, I think, roughly 3 to 4 months. And we only got through like 5% of our data set. So avoid manual input when you can. Some solutions are automate wherever possible. So try and use machine learning techniques like active learning or semi-supervised learning, or parallelize manual tasks across multiple people. So instead of hiring one person, hire 20, and you'll be done 20 times as quick. But yeah, human input is pretty much the ultimate bottleneck for a lot of processes, so eliminate it wherever possible. Yeah, so I'll just throw a kind of machine learning plug here to mention bottlenecks in machine learning pipelines because they can occur at different stages. If they can occur at data ingestion, which is when you're loading your data. That can either happen when you're loading data sets from storage or you're making API calls. It can also happen during feature extraction. So if you're doing expensive transformations, that can also cause issues. Or it can also be a bottleneck. Model training can also be slow if you have large models or slow optimizers, or your hardware is just not advanced. And inference can also be a bottleneck. Real-time predictions, in a sense, is a bottleneck if you're doing real-time predictions or deployment latency. But the main three are these ones. So if you have slow storage, you might have a bottleneck in your data ingestion. If you have a bad CPU or slow CPU, you might have feature extraction issues, and if you have a slow GPU, you might have model training issues. There are solutions to this, such as loading data sets can be improved by improving your hardware or batching. CPU issues can be improved by improving your hardware or using parallelization or algorithmic improvements. And then model training can be improved by optimizing your models, trying to use smaller models, or improving your GPUs. One thing I'll note is if you're training a deep learning model, avoid using the CPU. You should be using the GPU because that will be much, much faster. But if you don't have a GPU, then it will also work on your CPU. You should also use batch inference instead of one-by-one predictions to speed up production systems. But it again depends on your use case because if there's someone waiting for your inference, then batch inference won't work. But takeaway is each stage of machine learning has its own performance bottlenecks, and you should profile your program before optimizing. So you should first identify if data ingestion is taking the most amount of time, then you should focus your efforts on that rather than the other two. An example I'll give you is if this is taking 2 seconds and this is taking 2 seconds, but your data ingestion is taking 50 seconds, then a 50% improvement in the first one will reduce 25 seconds, whereas your other two, it would only reduce 1 second each. So focusing on the thing that takes the most amount of time will yield the best performance benefits. So how do we identify bottlenecks? So we've looked at what the bottlenecks can be, but how do we identify them? There's a couple of common techniques to identify them. The first is profiling. So this is what we did in our first couple of lectures where we used TimeIt in order to figure out the amount of time each line of code took, and then we would figure out where we should focus our efforts on. So that's kind of the example I drew previously as well. Another option we have is estimation. So in theory, what should be our slowest step? If we have hard drives, we know we're going to get roughly these read speeds. And if we have a data set of X size, then it's going to take Y seconds to load, and that's going to be our longest execution time in terms of our process. Our other option is A/B testing, where we try two different things and see which one works better. So that's just try A, try B, and see which one has the better runtime. But the takeaway is you can't optimize what you don't measure, so you should try and identify your bottlenecks. Yes, there's a raised hand.
Yeah, so when you're talking about the A/B testing,
Yeah.
how you actually do it, like version 1, version 2?
Yes. So it depends on also what you're trying to improve. So if you have, for instance, two hard drives, and they're rated for it's a bad example because hard drives are fairly clear in terms of their read speeds.
So could be iPhone versions,
Sorry?
different version of iPhone.
Yeah, you could try a different version of Python. I don't think in practice that's going to make too much of a difference. But one example is let's say you have fast storage, very fast storage, but it's over the network. And you have slower storage, but it's local. So this is computer one, this is computer two. You're running on computer one, but you don't know whether you should store your data set on fast storage over the network or on local storage, which is a bit slower. So you could try both and see which ones have better runtime. So is the network latency fine if you're getting faster read speeds?
So do you use any kind of tool for testing this?
Not really. So this would mostly be just done by using TimeIt in the same way.
Mhm.
You would just
Manually.
run both of them and see whichever one's faster.
Okay.
But yeah, a lot of this is kind of just problem solving and kind of finding the bottleneck. So it's the more kind of experience you have with computers, the more straightforward it might be. So in terms of approach one, which is profiling, there are lots of different profiling tools. We've looked at profiling in Python through TimeIt, which is right here. There's also cProfile. This might provide more in detail. It might either be more lightweight or might provide more details. And then in terms of Linux, You can evaluate network latency using perf, or it might be iperf. Perf might be to evaluate processes, and then there's also strace. So there's lots of different tools that you can use to profile programs and different processes. You can use profiling to measure the read and write speeds of your hard drives, measure the latency of your network. You can do all of that um, through programs. And then what you can kind of do is, let's say you have a function to load data from the internet, you can use time it to see how much time it takes. And then if calculating your features takes 1.5 seconds, but loading your data takes 30 seconds, then loading data is your bottleneck. And so the solution is first cache the data locally so you don't have to load from the internet ever again. But yes, profiling is the first step to optimization. The other approach we had was calculations. So this would be more so relying on theory and math. So using that predict performance. So let's say if our data has a size of 20 gigabytes, and we have three options. We have our internet speed, our hard drive speeds, and our SSD speeds. We can calculate and see that we'll get roughly 400 seconds. Well, it'll take roughly 400 seconds to load our data from the internet. It'll take 130 seconds to load data from hard drive and 40 seconds to load data from our SSD. So if model training only takes 20 seconds, then the disk I/O dominates, so upgrading storage matters. But if our model training takes 2 months, then upgrading from loading the data from the internet to an SSD is not really worth it. Because yes, it will save you 360 seconds, but in the context of 2 months, it doesn't really make a difference whether it finishes 360 seconds earlier. So calculations help you kind of, in theory, predict where the bottlenecks will be, but it's important to keep the improvements in context of the overall process. The other approach is A/B testing. So test different approaches to find the fastest solution. In A/B testing, you compare two implementations to see which performs better. The steps are implement two or more variations of a function or workflow, measure performance under the same conditions, and choose the best performing approach. For example, you could load the data from a CSV file, or you could load the same data from a Parquet file. And the results could be that the Parquet file is 5 times faster due to better compression and indexing. And so you would just go with that for storage format. When do you use A/B testing? It's when there's multiple possible solutions to a problem and where performance gains are uncertain, or when you want to optimize for real world conditions. So yes, in theory, this should be faster, but through A/B testing, we can actually validate it as well, because lots of things also affect runtime. The way that your data, um, the type of data that you have could also affect it. So if it's nicely organized, it could have one runtime, but if it's not nicely organized, it could have a different runtime. Another example is if you have 30 gigabytes of data stored in a single file, that is going to have a different runtime than if you have 300 files, each being 100 megabytes. So these two different scenarios are both 30 gigabytes, but they're going to have different runtimes. Um, I can't tell you which one's going to be faster because I think it does depend on what operation you're doing. For instance, reading files, one might be faster than the other, but if you're doing something else, it might be something else. But the point is, yes, in theory, these both are 30 gigabytes, so the read time should be the same, but real world conditions are different. So A/B testing does let you account for those as well. So how do we resolve bottlenecks? That's something that comes off it's sometimes a trade-off between three things. Yeah, so optimizing bottlenecks often involves trade-offs between speed, cost, and accuracy. So if you want something done quickly and of high quality, it's not going to be cheap. If you want something done cheaply and of high quality, it won't be done quickly. And so you do have kind of this trade-off. I won't say it's always the case that you have this trade-off, but in a lot of cases it is. So for instance, if you use lower precision models, so for example, if you use 16-bit floats rather than 32-bit floats, you'll speed up your inference, but your accuracy might be decreased. So you're sacrificing quality for um, having it done quickly with lower cost as well. Or storing compressed data sets saves space but may slow down access times. So optimization isn't just about speed, it's you also have to balance your trade-off based off of your goals. So how do we resolve bottlenecks? If we have memory bottlenecks, then our main solution is just optimizing the algorithm. Because memory is already so close to the CPU, the only thing we can really do is try and reduce the time complexity of our algorithm. If we have a storage bottleneck, then our solutions are to upgrade the hardware. So try and improve, upgrade the hard drive to an SSD or even an NVMe SSD. You could try and improve the amount of RAM that you have, so that you can start using RAM disks or you can store more data in your RAM. And you can also try and upgrade your CPU. That's not going to have as much of a benefit, but it could have a benefit in the sense that if you can do higher level of parallel, if you can have a higher level of parallelism, then you can reduce your runtime even further. Your other option is to improve how you're storing the data. So either using better formats or indexing or better file systems as well. In terms of network bottlenecks, you can optimize networking by using caching or compressing your data. You can also try and improve your networking speeds by upgrading your cables, improving your switches, improving your internet plan, things like that. And finally, if you have manual input bottlenecks, try and automate manual work whenever possible, either through machine learning or improve the runtime by hiring more people. But the best solution depends on the type of bottleneck. And yeah, moving on. Yeah, so we'll actually go through each one independently. So memory bottlenecks are typically caused by inefficient data structures, like using linked lists instead of arrays. They might be caused by algorithmic inefficiencies, like bubble sort versus merge sort. And this is primarily what we focused on in this module of data structures and algorithms. And so the solution is use efficient algorithms and optimize your data representations. So for instance, use NumPys rather than lists. In terms of storage bottlenecks, you can upgrade to an NVMe SSD. So there's hard drives. So hard drives versus SSDs. The main difference between these two is that hard drives have moving components, whereas solid state drives have no moving components. So that just means that hard drives have this mechanical disadvantage of having to actually physically read from disks, which takes time. So SSDs are just inherently faster because there's no need to move. Then we have two different types of SSDs. One are SATA SSDs, which use something called a SATA connection. So that's a type of wire and I think communication protocol. And SATA is also what hard drives run over. So SATA is fairly slow compared to the alternative, but SSDs are fast, so these together tend to be reasonably fast. SSDs also come in two form factors. So this is one form factor where it has a similar shape to a hard drive, and the other is a thin strip called an M2 drive. So M2 refers to the shape of the SSD, and it's like this long rectangular chip. These long rectangular chips do come in two formats as well, either using the SATA protocol, so it's the same protocol as, or same communication protocol as the SATA SSD, except it's in this format. And then you also have NVMe M2 SSDs. These SSDs are the fastest because they're almost directly just communicating with the motherboard and RAM. So typically M2 NVMe SSDs are the fastest. They're also the most expensive. But SATA SSDs and M2 SATA SSDs are also fairly quick. Hard drives are just the slowest, but they are also typically the highest in capacity. So if you want to, for instance, buy a 10 terabyte hard drive, or sorry, 10 terabyte storage solution, you're going to find the cheapest solution to be a hard drive. SSDs are going to be wildly expensive at this size. Other solutions are use RAM disks for temporary storage if you need to. Use indexed file formats, and then you should also be aware of what read speeds you are achieving on your drives. That can be done using the dd command, but I would also say be careful with this command and make sure you know what you're running, because it can also cause you to accidentally delete files and ruin your file system. Yes, there's a raised hand.
Hi.
Yes.
Yes, just a short question. When we are analyzing the storage bottlenecks, as you mentioned, in here, almost all of these are inside the server.
Yeah.
But there are also another because I used to work with external storage. So sometimes it's better when you connect an storage from the external, because they also have cache and they also can expand till petabytes of information. So when you are analyzing a storage bottleneck, is it also possible to connect to an external storage, right?
Sorry, I didn't understand. What's the alternative?
The external storage.
External storage. Okay. Yes. So you're talking about like a USB SSD, right? Or a hard drive.
No. The storage, like for example, from Dell or from IBM, is like a server but connected is directly to the server.
Okay. Is it local or is it over the internet?
It's local.
Okay. Yeah. So I think if you're like on a Linux system, at least,
Something like that. Something like that. Yeah.
you can treat the drive exactly the same as you would a local drive. So you would mount it to your system, and then you should be able to essentially do most of the things that you're doing here on those as well. Linux is nice in that sense where it lets you abstract a lot of things into kind of into fundamental kind of concepts. So even if your storage is over the internet, it's a different machine or it's local to your actual machine. If you're able to mount it as a drive or as a directory, then you're able to use this command in order to evaluate its read speeds. Using index file formats should yield benefit most, and you can also use it as a RAM disk. So if you're able to mount it and use it as a directory, then all of these should work.
Okay.
And yeah, I'll just also bring up that external SSDs and flash drive, external SSDs and hard drives are also a solution, but because they are over USB, they are going to be limited by whatever the read and write speeds of USBs are, or whichever one's lower actually. So if the SSD or the hard drive is slower than the USB protocol, then that's going to be the read speed, and if this is lower bandwidth, then this is going to be the limiting factor. But yeah, it's all about kind of knowing where your bottleneck is. And the reason I am focusing on this is because let's say you're working at a company, you're having to work with a data set and you find that you keep running into an issue where like it's taking too long to run your algorithms. So using these techniques, you're then going to be able to identify the reason the reason it's taking 3 days to get these insights is because we're storing everything on a hard drive. For $300, we could upgrade to SSDs, and then we should be able to get our insights in 2 hours rather than 3 days. So these types of reasonings are then nice to present to you, like your manager or whoever you're reporting to, in order to convince them to upgrade your hardware. Because at the end of the day, data structures and algorithms are all about reducing the amount of time that your algorithms take. And if your bottlenecks are coming from hardware, you should try and optimize those hardwares because those are kind of sorry, yeah, try and optimize those hardwares because those are kind of very detrimental to the overall process. Okay, so storage bottlenecks. You can also optimize data formats. So choosing the right data format can eliminate bottlenecks. For instance, I most often work with CSVs, but those are slow because they can be large and they have no indexing, and they store all your data in plain text. Parquet files, on the other hand, are fast because they're compressed, so they're smaller, and they're also indexed, so you can quickly find things because of these indices. And there's also HDF5. I haven't personally used either of these actually, but these are optimized for large data sets as well. And yeah, so this is just a code example of how you can convert your CSV into a Parquet file, and then reading the Parquet file is just much faster. The downside is that you just have to run this step, which could take a little bit of time. But generally, I think it's worth it to just use Parquet files if your work supports it. And yeah, optimized data formats can improve speed, sometimes without extra computing power. If you're running into network bottlenecks, some of the fixes is use wired networks over Wi-Fi. That's just going to improve your runtime or improve your network speeds because wired connections are more reliable. Upgrade to faster network cables. So if you're using Cat5 or Cat6, upgrading to Cat7 is potentially going to improve your runtime if you are maxing out your current cables. So this falls back to if it's not a bottleneck, you shouldn't upgrade it. You don't have to upgrade it. So if you have Cat5 and that's not being maxed out, then there's no point in upgrading. You're not going to see a benefit from that. Cache frequently use data when possible and use parallel downloads when possible as well. But overall, reduce reliance on slow external networks. Another option is choose the right compute resources. So your hardware can be a bottleneck or a boost. If you're doing lots of parallel processing and you want to improve the runtime, then you should get more CPU cores. If you want to load larger data sets without having to swap data between the disk, then you should get more RAM. And if you want to accelerate your deep learning, your actual model training, you should get more GPUs and TPUs. For instance, training a model on a CPU versus GPU, there's a huge speed up with GPU. Hardware upgrades often provide the easiest performance gains if it is a bottleneck. I think I've covered manual inputs well enough already, but avoid them. You should try and automate processes, run other tasks in parallel while waiting for input, or use AI-assisted tools, auto-labeling for data sets. But the best optimization for manual input is generally eliminating it. And here are just some cases of bottlenecks in real-world situations. So Netflix moved from on-premises data centers to the cloud in order to improve scalability and streaming speeds. So I think early on, Netflix had their own data centers where they stored all the data. They decided to move to the cloud because the cloud is more distributed. And so by moving the data closer to their clients, they were able to improve both streaming speed and then scalability as well. Google search optimized their indexing algorithm to speed up retrieval from trillions of documents. So this was a case where they improved the algorithm in order to improve their runtime. And in deep learning, I think this was OpenAI, maybe I forget which one, but deep learning, they were training GPT-3 and it required thousands of GPUs in order to avoid a long training time. So here they just bought thousands of GPUs. So industry leaders constantly optimize to remove bottlenecks, and so should we. And yeah, one thing I didn't touch on is this idea of using the cloud for your compute. A lot of the topics that we discussed today about like improving your RAM or improving your CPU, GPU can also be applied to using cloud resources. So in cloud resources, you provision your machine based off of the hardware that you need. But if you find that if your bottleneck is occurring on RAM, then you shouldn't try and improve the GPU for your machine by getting a new machine, because RAM isn't, sorry, if don't try and upgrade your GPU for your machine if your RAM is the bottleneck. So it does also apply to cloud resources as well. But the main kind of final thoughts are bottlenecks appear everywhere in data science. Optimizing one part might expose a new bottleneck. And so always profile first before optimizing, and smart hardware choices and algorithmic efficiency, both of these go hand in hand. Typically, you want to try and make it so that your hardware isn't, sorry, your hardware, when looking at your kind of slow hardware, so your storage and your network should not be the limiting factor for your programs. It should be your algorithmic efficiency, because those are your fastest components. And that's where you're gonna that's what you want to be the slowest thing in your program, is your fastest components. Okay, so yeah, the slowest part of your system determines the overall speed. So find it, fix it, and then repeat. And that's how you kind of improve the runtime of your program as a whole. Okay, so yeah, that covers the bottlenecks portion of today's session. And it also covers all of the material for this module. So yeah, I'm happy to take any questions for the next couple of minutes. But otherwise, yeah, that covers all the material for today. Tomorrow we'll have our case study, and yeah, hope everyone has a nice evening as well. Yes, there's a question, Saad.
Hey, thank you for this session. I wanted to ask you in terms of like during interviews, like, how
Yeah.
are these questions wrapped around?
Sorry,